Let me introduce myself. I'm Donny. I'm a PhD student from the Bandung Institute of Technology. It is in Indonesia. So we're actually an emerging group on quantum dynamics. So this is our, you can say, first paper in this specific topic. And this is the point of introducing driving is to see what can be extracted from the system, from the open quantum transport. If you if we say it in the qubit networks, so I'm saying that this is in the context or in the spirit of the quantum simulations in general. So let's see. But first, this is our recent papers, and I want to show the line of thought of how we come to these ideas, so we can see in the moment. And firstly, because I see that the open quantum system is not really taught in this seminar, so I want to talk about this topic in maybe some intuitive introduction. So don't take the cartoon so seriously, but they are in some kind of good. Yeah. So as we know that the decoherence or measurements due to the environmental interactions makes the relative phase broken. So basically, measurement is not required a conscious observer, so like human, but it's actually just any interaction with its environments. So in the experiment, you can see that decoherence is signed by the laws of interference patterns. This comes in many terms such as dissipations, dephasings, or relaxation. These are different but related to some sense. That in this topic, I want to stress dephasing and dissipation. Okay, so the open quantum systems, particularly I have to use the Lindblad equation, the completely positive map, as you know, or as we call the quantum channels nowadays. Yeah. So this is the unitary or Schrodinger evolutions, and the effect of the environment, the correlation with environment, is imprinted in the non-unitary terms in the Lindblad equations. But however, this is not all the story, because you see, this is limited to Born-Markov approximation. So we expect the environment effect is relatively small, which means that environment should be really big, yeah, compared to the system. And then the motivation of this work is actually a decade ago, that if you have heard about the quantum effects in the photosynthesis complex, so instead of decreasing the transport, so moderate dephasing noise can increase the efficiency. This is some kinds counterintuitive, but I will show you how the mechanism of this. The group of the Asbury-Gusick and I think Seth Lloyd in 2008, they modeled some kind of quantum work model. So this is the quantum part of the Brownian motions, if you think in that way. And our study is extending the environment-assisted model to contain a periodic driving field. And we will see it can improve the efficiency in some sense. And this is the, again, intuitive explanation of why quantum walk is more efficient than the classical random walk. As we can see in the classical random walk, the discrete graph is, for example, it takes 6 steps to reach the target here, and the quantum walk, because there are delocalization, in probabilistic sense, it is faster, at least quadratically, than the classical random walk. So faster walk translates to more efficient transport in presence of dephasing and especially dissipation. So we have to differentiate between the dephasing and dissipation here. The quantum walk mechanism can actually construct the universal quantum computers as we presented by Andrew Charles in 2009. So the core mechanism is just the delocalization. This is the reason why it is quadratically efficient than the classical random walk. And so, but in this case, we are actually talking about the cost system. So, if we want to talk about the efficiency, we have to move to the open quantum system because it will become sense if we talk about dissipation. So the reason that the efficiency is less than 1. Okay. And in this slide, I will talk about how dephasing can increase the efficiency instead of decreasing it. The core mechanism is the population uniformization. As we know that in the quantum regime, there are imprints of coherence in the population. What I mean by population is actually the steady state. So the steady state of the Lindblad equations should be uniformized as possible to get this enhancement. So this enhancement doesn't usually come if the trapping rate is too low or too high. So the conditions have to just fit such that the population can be uniformized. For example, if the efficiency without the noise is already high, the ENAQT or the enhancement is not really big. And in some other cases, there will be monotonic, so there will be no peak at all. So this is the dubbed as the ENAQT. But in this talk, I will extend the model to contain the driving fields. So I have to note some caution here that we do not attempt to explain the photosynthesis in vivo. Instead, we have the spirit is just how to take the benefit of the phenomena to the quantum simulations. For example, the trap ions or the laser-Wootton waveguides. And I will talk about the possible experimental realization before the conclusions. And yeah, we use time continuous models instead of the discrete one like in this cartoon. So this is the setting. Our setting consists of n, we choose 3 for simplicity, and qubits. And the excitation starts from the side 2, and this is the excitation will be trapped in the last side. Remember that we also introduced the dissipation in all the sides. So, and dephasing also in the sides, where the dephasing is actually just a projective measurement, and the trapping, actually we can omit the trapping and calculate the steady state population in the nth side with integrating from 0 to infinity, but I think it is more intuitive to do it this way. in the first model, the driving is taken on site, meaning that it is altering the energy of the on-site energy of the qubit, and in the second model, the driving applies to the coupling. So when the coupling is not driving, it becomes usual model, the usual tight binding model. And we also take omega to an ordered site, so the disorder is not important here. This is the interesting side, because initially ENAQT thought as because the existence of the Anderson localization, and dephasing comes to solve the localization, to destroy the localization, and just giving a small moderate efficiency gain. But it turns out that without any disorder or any quench disorder, ENAQT still persists unless it is end-to-end side transport. So we initiate the excitation, in this case, in the side 2, and the driving. And the driving is, we choose coherent driving, so it can be chosen another, but at least the periodic or quasi-periodic is okay. And we can see before the result, we perform two kinds of method. One is analytical and one is numerical. But in the analytical, we can only approximate the steady state because we currently truncate the approximation to the second order. So we can skip this bus for the analytics. So the result is that if we apply the driving uniformly to all the qubits, so no effects can be observed, because analytically you can transform to a rotating frame and get the exactly same Hamiltonian except for the diagonals. And the important thing to notice first is that the DAOQT, or the driving assisted open quantum system with DAP here, is really dependent on the driving rates. So wherever the trapping is too high or too low, or the dissipation is too high, there will be no efficiency at all. And the DAOQT, which we define as the distance between the efficiency and the one that the efficiency with dephasing phase with dephasing rate set to 0. So here we got the result for the model 1, or for the on-site driving, that we have the efficiency gain of about 6 to 8%, and in in a quantum zero regime, it will vanish. So we are interested on how the driving could affect the transport, and it turned out that our analytical method is only good for high driving frequencies, because if we want to cover these regions, we have to cover many terms on the FMM expansion. And you can see that if the driving is very high, so the evolution, this is the time evolution is governed almost completely by the driving, and we got the average situation. So where the driving is, sorry, where the efficiency is averaged out because of the driving. And in the second model, we can see that the efficiency is actually higher in near the coupling rates, and this is, we have some kind of interesting oscillating pattern in the efficiency gain, and we will see why this can occur in the model 2, and in particular cannot occur in the model 1 because the population congestion mechanism. And yeah, so in this case we only got 8 to 10%, but this number can be higher or lower because the interesting pattern is not covered by the FMM analytical method. So we have to try just rather guessing some dissipative and trapping rates. So in the future, maybe we can do better. And the point is that actually this is the behavior is because the population, we call it population congestion, but this is the population dynamics of the site 1 and the site, the initial site, which is the site 2 population, the middle site, and the site 3, which is connected to the drive population. And as you can see that the end-driven case is oscillating and exponentially vanishing as expected. But the interesting thing that if we consider the local maxima here, the global maxima, the second maxima, or the global minima, as you can see here, that there are some kinds of congestion pattern in the population. So how the driving can drive the population to the right side. What I mean by right side is the third side of the transport. Is the if we give the right driving frequencies. In this case, it is close to.
We have about a minute left, Donny, just to let you know if you're going to also accept questions.
Mm-hmm. Sorry for that. I forgot the time. So, and the model 1 and model 2 can be realized in some experimental realization. For example, in the Rydberg atoms by varying distance between the sites, and in the waveguides by manipulating the refractive index, and some others. So
this is great. Actually, this was one of the questions already, so that was good.
Sorry. Yeah. So after that, this is not related directly to the. I can jump to the conclusions. So, and to connect with the other, we are open to the suggestion on how this phenomena can benefit any noisy device or the quantum information processing in general. So I hope that clear enough. Thank you.
Thank you very much.